All right, so in this first video, I'm going to cover the math behind the M constraint. I find that a pretty interesting topic to cover first because it really helps understanding or solidifying your knowledge of matrices, and especially the structure of a matrix and like the data that's contained inside of a matrix. And when I say matrix, I only mean transformation matrices, so 4x4 matrices. Yeah, I will not really go in depth on any of the vector math that I'm going to be using. So if there are some things you don't really understand, I'm going to have links in the description that kind of go over that. Cool, so let's actually jump into it. We are going to define 2 points that we'll call A and B. These points can be anywhere in space. And the goal is going to be to build the matrix that represents this transform. Like so, right? So we'll have x pointing to B, towards B, then y will just be perpendicular to x, and z will just be perpendicular to these two other vectors. The matrix that actually represents this, or any transforms really, is contained in the first row, the x vector, so x, y, and x, z. And the second row would be y, x. Let's write that smaller over here. Y, and y, z. Cool. Then the last row would simply be z, x, z, y, and z, z. That matrix that we have right here already encodes a lot of things. It encodes three things really. Simply by listing like these three vectors, we are first of all encoding the orientation of our object, just because the way each of these vectors are oriented, like in relation to each other, just define a specific orientation for our transform. Then the second thing that's encoded in there is the scale. If we had a vector x that would be twice as long as of length 2 basically, then that would just mean that our transform would be scaled twice on its own x-axis, right? This vector right here would have a length of 2. Cool. And then the last thing would be, if I just remove that y vector temporarily and draw it like this, right? So this y vector is not perpendicular to x anymore. This is what's called shearing. Shearing is really something you want to avoid in most cases in rigging. Yeah, because especially in the case of an M constraint, right? You want to have your setup modify the orientation of your object, but you definitely do not want your object to scale or to shear, because that would kind of deform your object, and that's really not what an M constraint should do. So we'll really work towards maintaining that the length of these vectors to a length of 1, and to maintain like the orthogonality of each vector to each other vector. Cool. So yeah, we have a 3x3 matrix. I was saying earlier that we wanted an actual 4x4 matrix, and that's because in the last row, we can actually store the position of our object. So our transform is placed on the point A, so we'll just store A like this. So a y and a z. Cool. We technically are storing everything we want, but we are missing one last column. I won't really go over why it is 0, 0, 0, and 1, but you just have to know that this is what that last column is. I know it's useful for the math under the hood. I think it defines that these are vectors and this is a point. It might, I know it's also used like in graphics programming to for like projection matrices and that kind of thing. Again, you really do not have to worry about that. Just know that this is always going to be 0, 0, 0, and 1, and you are grand. Cool. So with that defined, I'll put that on the side, and we can actually start, well, solving our vectors, right? So let's, I'm going to draw that a second time. So that's going to be A, that's going to be B, and let's first solve our x vector, because this is the only thing we can solve at this point, right? We just have two informations, 2 points defined. We do not have any data to solve any other of the other vectors. So I'm going to define the vector x as simply b minus a, because to define a vector that goes between 2 points, you just subtract the source from the target, or like the origin from the target. So that's b minus a, and the vector that we've solved right now is not normalized. I think the math notation for a unit vector is a little hat on the vector. It could also be specified as the vector divided by its own length. But I'm not really going to worry about that, and just whenever we want a unit vector, I'm going to note it as a vector with a little hat like that. Cool. So we've got x. This is the first row solved. Then what do we want to solve? Ideally, we would want to solve either z or y. But again, we really do not have the data to solve that at this point. So what's typically done in any M constraint is you can specify an up vector. The up vector is can really be anything, and I'm going to draw that in yellow actually. It can really be anything. It could point in that direction. It could point in that direction. There, you name it. The only thing it cannot do is be on the same line as the x vector, right? It cannot be collinear with x. The reason being, and I'm simply going to kind of define it as the vector that goes, I don't know, let's say it kind of points. I'm just going to have it straight up, and I'll purposefully have it longer because we do not need that vector to be normalized. The thing you typically do in rigging is you define that vector as the vector that points towards another object. So let's just define a point C right here, and we'll define our, I'm going to call that the U vector, and this time I'll use an arrow because this is not normalized. We do not need it to be normalized. We could normalize it. That wouldn't really change anything. But I'm going to note it as C minus A. And that's pretty much it. The reason I was saying it cannot be collinear with X because by having two vectors that are not collinear, we are defining a plane. So if I actually draw that a bit better, right, this is the like a portion of the plane that goes through U and X, and any plane has a normal, and that normal is our Z vector. Yeah, no, let's just draw it like that. That's fine. The way you define a normal is using the cross product operation. So we could have any two vectors on that plane and do the cross product between those two vectors, and we would get the Z, our Z vector. So the cross product is simply our X with the vector U. And that's pretty much it. There is a good chance whenever you do a cross product that you are getting the opposite vector to the one that you want. In this case, I know because I've tested it that this is X cross U. But yeah, if you notice some kind of like weird rotation values or negative scaling, in your object. This is probably because you've done the cross product in the wrong order. So just swap those two vectors and you'll be grand. You'll have the vectors you want. Again, this is a normalized vector, so I'll have a little hat on it. And yeah, finally we have our a new plane, right? Because we've defined two new vectors, so that defined a new plane. And that new plane has our y vector as its normal. So we'll do y. Y this time, again, I know the order of the cross product already because I've tested this. And this is z cross x. Right, so the normal to the plane that goes through z and x. And again, we want that normalized. So yeah, that's pretty much it. Again, because this is a cross product, we might be getting this one. I know that this is actually z cross x, but depending on the setup that you do, depending on what vector you use as the source, you might need to mess around with the order of the cross product for both these two vectors. Cool. I think that's pretty much it. We have our three vectors. We've got them all orthogonal to each other. We've used a temporary up vector. Just a note again, this one can really be anything. I think Maya defines by default, if you do not specify a world up object, you would have that vector be 0, 1, 0, which is the world up. But again, it can really be anything else, so long as this vector is not on the same line as x. Cool. Yeah, that covers pretty much everything. In the next video, I'm going to actually implement that in Maya. And yeah, I'll see you there. Bye.